Hi everyone, we are back and we are on our last lecture, which is fitting, regressions, and confidence bands. So again, we touched about at the beginning of this course and we've done a lot of different tests, but we've kind of avoided a lot of kind of discussions about fitting, regressions, and we mentioned at the very beginning that we want to fit things with appropriate functions that are physical in nature and to determine whether they are a good fit. And with the exception of our chi-squared goodness of fit test, we haven't really talked about distribution, shapes, and fits. And the methods in which that we analyze whether something is a good fit or not. So we're going to talk about one of the most popular types of fit analysis, and that's regression analysis. And one of the most popular techniques within that broad category is the method of least squares. So in the method of least squares, we're going to be working with two variables, x, which is going to be the independent or input variable, and y, which is the dependent or the response variable. Typically, we can assume that the total uncertainty in y is going to be much greater than that uncertainty in x, which is a pretty reasonable assumption when you're doing your analysis. So if we're fitting this based on a linear curve, y equals a plus bx, a and b are going to be our fitting constants. So our error is going in predicting a y value will simply be the measured versus the actual response. And we want to select a and b such that our error is as close to 0 as possible when we sum all of those number of points n in order to minimize essentially the error. So this is your response. This is basically what the fit of the y value should be. So the principles of least squares will give us this value here, and you would fit effectively your curve as such. So you can define some critical values. So this is the sum of squares in the x, sum of squares in the y, same idea, and sum of the square in the xy. And so we can calculate the error sum of squares, which we're trying to minimize, and they're described effectively here. So this calculation will give us those fitting parameters, and we can also obtain estimates of the confidence intervals for those fitting parameters as well. So again, this is kind of the behind the black box that spits out essentially how our fits are conducted, and what's the rationale behind it. How do we essentially get those linear lines? We'll do some examples in R in a bit, as well as some confidence intervals for those fits. You can also do nonlinear fits as well. So you can perform this type of analysis on exponential, logarithmic, polynomials, and beyond, not into infinity and beyond. But you can do the same type of analysis essentially to achieve that. Now, a lot of the method of least squares, it's much more difficult to perform this analysis on some of those fits, but we have other tools and correlations and basically values that we can use in order to see about, is it a good fit or not a good fit. So one of our values is essentially correlation. So we've assumed the total uncertainty in x was small and close to 0, holds, but there are a lot of real-life scenarios where this is not true. So when we're plotting x versus y, in the most general sense, is to observe, are the variables correlated? So one of the ways that we can tell whether these variables are correlated is with our correlation coefficient r. So this is just beyond, again, fitting and method of least squares, but we're going to look at, are the variables correlated? So we can take our previous definitions that we defined, and if r is equal to 1, we have perfect positive correlation. If r is negative 1, we have perfect negative correlation. If r is 0, we have no correlation. So there's no linear association. Again, this is for linear fits. You can also do r squared. Now that value varies from 0 to 1, and you can see the definition here. This tells you, again, if our r squared is 1, then that is perfect correlation, and basically our fit is excellent. If it's 0, our fit is not excellent. So remember, when you're fitting, make sure that you're looking for some of these parameters, and again, know the difference between our sum of squares and getting those best fits, and again, how we calculate those, even though we're going to be using a lot of functions and programs to do that for us effectively, and how to interpret those. So r versus r squared is very important and tells us a lot about kind of the different parameters that we're working with. So we'll see you next time in R to actually go about the process of fitting these functions. So we'll see you then. Thanks. Bye.